My name is Małgorzata Łazęcka, and I'm a postdoc now at University of Warsaw. But I obtained my PhD from Warsaw University of Technology, and I'm going to talk about my PhD thesis, at least some of the results from my PhD thesis. And my presentation will be about resampling methods in conditional independence testing, and I will talk a bit about some measure of dependence coming from information theory, and I will show you how to use them to test conditional independence. Okay, so let's start from the notation. In my presentation, all the random variables will be discrete, and I will denote them using x, y, and z. They all will have finite supports, and all triples x, y, and z, the probability of obtaining them will be greater than 0. And I will denote conditional independence using that symbol, and it means that x is independent of y given some additional variable z. And it basically means that the joint distribution of x, y, and z factorizes in the following way. So px given z times py given z times pz equals the joint distribution. And just to give you some maybe intuition on that, I prepared a very easy example when the conditional and unconditional dependence or independence are not the same. So when the temperature outside is high, when it's summer, many people go on holidays and they spend time somewhere swimming in the lakes or seas, and there are some cases of drownings during that time, and also we eat many ice creams during the summer. So the two, drownings and ice cream, are not independent, but if we include some additional variables, for example, temperature outside, then they became independent, because now we know something more, that the common cause of these two things. So this is an example in which these two, conditional and unconditional dependence, is not the same. And why do we need that testing of conditional independence? So again, just an easy example of application. I'll give you just one example, but in fact, there are many, many more. So for example, we can use conditional independence testing for feature selection. So we ask the question if y is independent of x given some variable z, and in this setting, y denotes a response variable. So we want to somehow model y using some additional variables, for example, from z1 to zs. These are variables that we believe are relevant for this task. And we have an additional candidate, which maybe we should include in the model, but maybe not. So we ask a question if these two are independent given variable z. And if the answer is yes, then it means that x does not contain any additional information about y, which is not included in z's. So we should throw x away. X is redundant, and build a model based only on z variables. And if the answer is no, so they are dependent, even if we include z's, then probably we should include also x in our model. Of course, this is just one way of selecting the features, and maybe not always the best way to do that. Okay, so in our example, y are drownings, x are ice cream, x is ice cream sale, and z are these additional variables which we can take into account, for example, temperature outside. And in this case, the answer is yes. These two are independent given the temperature outside, so we don't need x in our model. Okay, so now I'll talk a bit about a measure of conditional dependence. We want to somehow measure how strong the dependence is and know if there is a dependence between two variables. And there is a measure called conditional mutual information, which comes from information theory. And it is basically a Kullback-Leibler divergence between the joint distribution and the factorized distribution. And that measure has two important properties. The first one is that it's always non-negative. And the other one is that it equals 0 if and only if we have conditional independence. So if that measure is greater than 0, then we know that the two variables are dependent given the third one. And if you want to test for conditional independence, this is of course very useful property. Okay, and we want to somehow estimate that measure, that CMI. And there are many approaches how to do that correctly in case of discrete random variables, mixed variables, continuous variables. But I'm going to show you just one way how to do that, because then we have some asymptotic guarantees on that estimator that we obtain. So the estimator is really easy. We have to first estimate probability mass function, and we do it just by using fractions of our sample. And then we plug in that estimated probability mass function into the formula. We can treat CMI as a function of probabilities. So we can now, instead of using the true probabilities, use the estimated probabilities, and that's all. And now we can move to testing conditional independence. So we want to, so we have the null about conditional independence, and we have the lemma which states that if we have conditional independence, then we know asymptotic distribution of that CMI statistics, and it is chi-square. And if it resembles you Pearson chi-square test, it's a good intuition, because it is basically very similar test. The asymptotic distribution is the same, and asymptotically these tests are equivalent. So you may think of it as about Pearson's chi-square test, in fact. And that test based on CMI statistics is called G-square test usually, and this is basically a likelihood ratio test. And yeah, and it uses the test uses this lemma about asymptotic distribution of CMI hat. And you probably remember that there was that rule that we need 5 observations per one distinct value in our observation, in our sample. And here for conditional independence testing, it is a problem, because if Z is multivariate, and it might be multivariate if we have a big model and many variables in it, so then we fall into multiple testing problem and because of dimensionality here, and it is not that easy to run the test because it usually is far away from its asymptotic distribution. The distribution of the statistics is far away from the asymptotic distribution if the sample size is small. So this is one reason why I'm going to use resampling methods. And another reason is that usually we can use, instead of using CMI, conditional mutual information, we can use some kind of approximation of it. And in a form of, and we can use it in a form of generalized feature selection criteria. And basically it means that we, instead of using the full conditional mutual information, which includes all the interactions between all the variables, we just set some, we ignore some interactions and just put more weight into some lower level interactions. And it is easier to estimate, but unfortunately, it is much more complicated in theoretical way. So here is the same theorem for the criteria. And as you can see, there's a problem that we don't know the exact distribution. it can be either normal or weighted chi-square. We don't know the parameters of the distribution. For example, here is sigma square, which is not known, and it depends on the distribution, but we usually don't know the distribution of our data. And this is the second reason why we want to use resampling. I won't show you the results for the criteria later, but this is just the justification why to look into these methods. So about resampling now. I will denote a sample using xi, yi, zi as previously, and I will use stars to denote a resampled sample. So with stars, it is always a resampled sample. And as you want to mimic the behavior of a sample under conditional independence, we want to keep the distributions, the joint distributions of x and z and y and z unchanged, and only break the dependence between x and y given z. So we want to just break the dependence, that conditional dependence between the two variables. And I will consider two scenarios to do that. One is called conditional randomization, and another one is conditional permutation. And they are both from literature. I didn't create them. Okay, and maybe I'll show you on an example how they work. So we have a sample, x, y, and z. And in a resampled sample, we copy y's and we copy z's, and we sample only x star. And we sample x star in the following way. So we have now z's, a star that we have, and for each layer of z, so for example, here z that is equal to 0, we sample x star from the distribution, from that conditional distribution px given z equals to 0. We assume that we know the distribution, and we can sample, and using that, we can sample x star for each z separately and independently. And for conditional permutation, we do almost the same thing, because we also copy y's and z. These are the same vectors as previously. And now, instead of resampling x star, we permute x star. So here we have 1, 0, 0 for that layer of z. And here are the permuted values of x star, so 0, 0, 1, for example. And we do that for each layer of z independently. Okay, and now we are interested in the same as for a sample. So we also want to know what is the distribution of CMI computed on a resampled sample. So first we estimate probability mass function, p hat star, for a resampled sample. And then we compute CMI for a resampled sample just by using these probabilities estimated based on a resampled sample. And first, we will obtain the asymptotic distribution of p hat star. I'll show you the theorems for CR, so conditional randomization and conditional permutation. I'll focus more on conditional permutation because this is the more interesting case. And then for CMI, I just conclude that we will use the delta method, and it will be easy to obtain the distribution for CMI hat star. Okay, so let's start with p hat star. So this is the lemma for conditional randomization, and this is a result for the whole vector of p hat star. So it is not just one value here, it is the whole vector of all the probabilities for all the values. And this is why here we have covariance matrix. And the proof is quite easy because all the observations are independent and we can just use Berry-Essen theorem. And for permutations, we have almost the same theorem. We have to center our vector in a different way, and the covariance matrix is different, but the proof changes dramatically, because now the observations are not independent, because if we permute observations, then if we use one observation, we cannot use that observation again. And this is why that case is much more difficult than the previous one. Let's focus on simplified case. We don't need that conditioning now. Let's assume that we are in one layer of Z. So Z is constant and we take just X's and Y's. So now we have a sample which is just X's and Y's, and a resampled sample with X is permuted and Y is copied. And in fact, randomly choosing permutation of X is equivalent to randomly sampling the content of the table while keeping the marginal values fixed. So in each row, we sum the values in that row, and this is a fixed value. And now we sample a content of the table, and we want the distribution of the whole content of the table. And actually, it wasn't no result. What is the asymptotic distribution of that? The only thing that was known was the asymptotic distribution of one element of the table, because then it is it has hypergeometric distribution, and it was obtained in 2007. And for the whole table, we obtained the distribution of that thing. It is similar to hypergeometric distribution, but in fact it is generalized and multivariate hypergeometric distribution. If we had just one row on just one column, then it would be well-known multivariate hypergeometric distribution, but as we have the whole table, it is somehow generalized further. And we obtained the distribution of that, the asymptotic distribution of that. And moving to conditional case, it is in fact...
sorry, you have 3 minutes more.
Okay. So for the conditional case, we use that theorem many times, and we obtain the distribution. And now we can obtain the distribution of CMI hat star using that. We know the distribution of that guy, P hat star here. And basically, we have to show that these two first terms vanish, and that the distribution is based on the third term. So now we know that the distribution of CMI hat star is the same, in fact, as for our sample. Okay, and non-asymptotic viewpoint. So this is a completely different viewpoint on that problem. Now we also have a sample, and we have big B resampled samples. And if the null holds, that lemma says that p-values obtained in the following way are valid p-values. So we can use them to test the hypothesis of conditional independence. And that result is intuitive and based on exchangeability. So if we have conditional independence, then using these two resampling schemes, we in fact don't change the distribution of the data. So we also don't change the distribution of the resampled statistics computed based on the resampled data. So all of these statistics have the same distribution, and as they have the same distribution, we can reorder them, and any ordering is equally probable. So that guy here, that p-value, is uniformly distributed on the discrete set that is written here from 0 to 1, in fact, but it is discrete because of the number of resampled samples p. Okay, and now simulations, very quick. How can we use these results? So first of all, I will show you how to test conditional independence. We have that asymptotic test, which is well known. We have that non-asymptotic approach. I will call it exact. So it is based on these p-values. And we can use another test, which I will call DF estimation, in which we use the asymptotic distribution chi-square, where we estimate the number of degrees of freedom here based on the resampled samples. And now the top panel show you the problem that is with the asymptotic test. So we exceed the significance level for small sample sizes. In fact, the x-axis means more or less how big the sample size is. So here's that 5 observation per distinct value in our data set. And you can see that even for 5 observations per cell in the table, the significance level is exceeded. And this is because the number of degrees of freedom doesn't change. Even for some small sample sizes, we use the same distribution, which is the asymptotic distribution. And maybe if we use the number of degrees of freedom based on the resampling, our performance will be better. And it is shown here that the blue dots are much closer to the red one than the horizontal line. And here it is. Now there's no problem with exceeding the significance level, even for small sample sizes. These are plots just for small sample sizes. And here is the power of our procedures, both for conditional randomization and conditional permutation scheme. The strongest dependence is on the left, the weakest dependence is on the right. So the power is also smaller here, but we can see that we can detect the dependence between the variables. And one more side note on the criteria. We have here CMI, so that conditional mutual information, but we also have here GMI, which is a criterion of feature selection. And as you can see, the power of CMI is much lower than of GMI, and it shows that the criteria are very useful, although the theoretic results are not as simple as for CMI, and there are many approximations on our way to finally decide, make a decision based on a test of conditional dependence. Okay, and here are the conclusions. And thank you very much.
Thank you. Is there any question? Just a quick one. Yes, Zhikica?
Thank you, Maria. Well, there is quite a philosophical question from my side. So you mentioned that the basis of your test is conditional information, and which is based on Kullback-Leibler divergence. My question is, can we modify this? So we use, for example, Jensen-Shannon entropy, and have you tried it? Probably. That's the question. Thank you very much.
Thank you for the question. I haven't tried it, but I think it is possible, but I'm not sure about these distributions, either asymptotic or not, because to run the test, we need that. Sorry, just a second. Okay, here we are. We need that asymptotic distribution or not asymptotic distribution of the measure, and I'm not sure about these results for other measures that you mentioned. But basically, if there are results on that, there is we can run the test based on that.
Okay, thank you.
Okay, we have one more question in chat. How applicable do you think these arguments from the proof about the resampling distributions would be for other conditional independence tests?
These results are very depend on conditional mutual information, and that it is a nice measure of the dependence, and I'm not sure how transferable it is for other measures. For sure, it is not transferable for the criteria. For the criteria, the results for resampling are even more messy than for that case for the sample. So this is the result for the sample for the criteria, which also should somehow measure conditional dependence. And for the resampling, it is even more complicated. So I'm not sure how transferable it is.